Okay, little practice exam. The first one here, make sure, this following instructions, bonds broken, bonds formed type stuff. Terminal alkyne reacting with HCl makes the hydrogen go to the less substituted carbon. Chlorine adds. Pi bond reacts again. Now it's just, again, same idea. More substituted carbon. You can do resonance with this. Chlorine adds. Just bonds broken, bonds formed type stuff. Draw a resonance structure. Make sure you draw a resonance structure. A lot of people start doing reactions, breaking sigma bonds. Don't want to break sigma bonds here. You want to do resonance, which means only moving electrons in p orbitals. So there's the resonance with the lone pair there. This is the more stable one because everything has a full octet. So that's the more stable one. Number 3 here, challenging one. Got to recognize this reagent really means Na plus NH2 minus, right? So recognizing that, there's 2 equivalences, and the product is an alkyne, so it means you have to, you're going to do 2 E2s, but what would you need to have to make 2 pi bonds? You need 2 leaving groups. So you do 2 E2s, and that gets you to this. Then from here, you take that terminal alkyne, and you can notice here there's 1, 2, 3, 4, 5, 6, 7 carbons. So there's an extra carbon was added. One way to add carbons is to deprotonate a terminal alkyne, make a minus charge there, and then do an SN2 that adds the carbon. That gives you this internal alkyne, which then you can use H2 palladium on carbon, which takes it all the way down to the alkane. Let's see, so for this one, just basic tautomerization in acidic conditions, tautomerization in neutral conditions, bonds broken, bonds formed. Know that you're going from the enol to the ketone, the cetobondo. So pretty self-explanatory there. Make sure, right, if you're in acidic conditions, you use the acid. If you're neutral, you don't. If you're basic, you use the base. Make sure you use the most reactive species. Let's see, number 5 here. Again, alkyne, terminal alkyne. Add HBr, make a carbocation. You add the H to the less substituted side, right? There's H's already. And then because you're in a polar protic solvent, you have water, you're going to add the water. Now you're in acidic conditions, you have an enol, so you're going to do tautomerization. If you notice that HBr is a catalyst, that means you need to add H plus, Br minus, right? And you don't need to show the Br taking it. Same difference is fine. Enol, get to the cetobondo, deprotonate, get the product. Number 6 here, this one is about understanding what ortho, meta, and para mean, but also understanding where you can add things. So, as meta to the cetobondo, so this is the cetobondo. So from here, ortho, meta, and then para. But you can't add to this meta position because there's already something there. That's not a hydrogen. So you circle this by bond, something would add there. Electrophile adds para to the ethyl. So there's the ethyl. Orthos, metas, and the para. So this would be the pi bond where the pi bond's at, where the para is at. That's the pi bond that would react. You're adding something there. Label the substituent in the molecules below as electron donor, electron withdrawing. Electron withdrawing group, the carbon here doesn't have, it's electron deficient, it's attached to 2 oxygens, so it's electron withdrawing. Alkyl groups are electron donating because of hyperconjugation, no resonance, but just hyperconjugation. Lone pairs in the nitrogen, electron donating. Lone pairs on carbon, electron donating. And then lone pairs in this oxygen, electron donating, even though it also has a resonance that pulls it away. So now to rank these, so I always like to do the range, right? Find the extremes. The most electron withdrawing, so the least reactive, right? Because remember in these reactions, electrophilic aromatic substitution, the ring is the nucleophile. So the ring is the nucleophile. So pulling electrons away makes it less reactive. So electron withdrawing groups make it less reactive. So that'd be the number 5. This would be the most donating because that's a negative charge, most likely to donate electrons in. Then I had nitrogen is ahead of oxygen because nitrogen's less electronegative, so more likely to donate. Oxygen holds electrons tighter. So 1, 2, 3. And then this is doesn't have any lone pairs, there's no resonance, but it's still better than withdrawing. So draw the mechanism for the reaction below and add the missing product. So for this one, all we're doing here is, again, electrophilic aromatic substitution. The ring is the nucleophile, right? And if you look at the product, the thing that adds is ortho, right? So that means we need to use this pi bond, right? 2 arrows, so it's an addition step. We make the sigma complex, which is just the fancy word for the intermediate of the reaction. We do the elimination, where the H comes off, right? Because remember, we're doing the substituting in H with whatever we're adding. And so then we get the final ring, and we get H+. So then I ask you, redraw the first sigma complex below and draw all possible sigma complexes, including arrows. So this is just a fancy way of saying, take this sigma complex and draw resonance structures. I'm just asking for resonance, right? Resonance arrows. So all I'm going to do is just do resonance structures. So the first one I did, I had the electrons go here, right? So the nitrogen is a plus charge. Everybody has a full octet. That's actually the most stable one because it has a full octet. Everybody does. And then I moved electrons from back in the ring out towards it. So the plus charge there, pi bond there, plus charge there, and there's the 1, 2, 3, 4 of them that you can see. You could have done it a different way to get to these, but that's okay. If you wanted to redraw this and do this, and then redraw this and then do these, that's fine too. However you want to do it to make it as clear as possible, it's fine. More resonance, so just drawing some resonance structures. So in this case, the only thing you can really do, right? You can't do there's no lone pairs here, so oxygen lone pairs outside the ring, pushing electrons in, electron donating group. Right, pi bond, pi electrons go to an atom. Right, make sure you draw the negative charge on the electrons. Boom, boom, lone pair there. No charge anymore. Nitrogen has 3 bonds, no charge. Boom, boom. So pi bond into the atom. Negative charge there, lone pair, plus charge again. So the charges stay balanced throughout this thing. So make sure you're always balancing your charges as well. Make sure those arrows, when you're making a pi bond, the arrow goes between atoms. When you're moving electrons to an atom, make sure it goes directly to that atom. Some aromaticity questions. So first we got to do some hybridization state. What hybrid orbital the lone pair is located on? sp3. It should be sp3. If it's not sp3, that's wrong. It should be sp3. That is definitely sp3. I'll fix that in the key. There's no negative pi bonds. sp2, and then p orbital. And then we want to label each molecule as aromatic A, anti-aromatic AA, non-aromatic Na. A, so this first one's aromatic. It's a ring, uninterrupted system. 1, 2, 3 pairs of electrons, so it's aromatic. This one is 1, 2, 3, 4. It's all in a ring. They're all sp2 hybridized. It's all planar. It's all p orbitals, but it's an even number, so that's anti-aromatic. This one is a ring, has an even number, but it's broken up. It's not an uninterrupted system. So this is non-aromatic. This one's aromatic, 1, 2, 3, ring. This one's non-aromatic because, again, it's an interrupted system. There's sp3, doesn't have any p orbitals there. And then finally, this one, uninterrupted in a ring, 1, 2, 3, 4, 5. So that's aromatic. And because it has 5 lone pairs, that's equal to 10 electrons. So that's what we have there. This one, looking for the mechanism, missing product from the first reaction. Cl2, make sure you draw the 3 arrows. Right? Make sure you draw the 3 arrows because it makes that 3-membered ring. Make sure you have your bond angles good. It's a polar protic solvent, right? So you gotta be aware of those polar protic solvents. That's what's gonna add in, right? Protic solvent. It doesn't matter which carbon it adds to because it's symmetrical, and they're both equal substitution. So you can pick whatever. I mean, I put it over here, but it adds in. Now you're gonna need to do a deprotonation step. That gets you to this alkene. Then we have this alkene, Br2 now, but same idea. 3 arrows again, 3-membered ring. Or your wedges and dashes now. This ethyl and this O-ethyl were both wedged on the same side. Chlorine and this ethyl on the same side. So you gotta use those wedges and dashes. In this case, bromine could have gone to either place. I had to go here because that's why I had it, just to match the product. Adds there, bounces up, SN2, you get that trans. So make sure you understand biggest things, 3 arrows. Notice here, there's no It's a polar aprotic solvent, so that's not involved. So it's aprotic solvent. So the Br minus can come. Make sure you have the 3 arrows, and make sure you have your wedges and dashes and things lined up correctly. And don't forget your bond angles.